But I think from a more geometric perspective, to make it clear exactly what the hell was going on with all these eigenvalues and eigenvectors that showed up when we started solving these equations. So last time, you might not have even caught this because it went so fast, but last time essentially we showed the following theorem, or at least I argued the following theorem, which is that if A is a 2 by 2 diagonalizable matrix, and for the purposes of our conversation today, everything is going to be 2 by 2. A lot of the complications of the higher order stuff are present in the 2 by 2 case, and I can teach you about 2 by 2 matrices. There's no way we have time to talk about n by n, the sort of general case here. So if A is 2 by 2 diagonalizable matrix with, say, eigenvalues lambda 1 and lambda 2, and eigenvectors v1 and v2, then the general solution to the vector differential equation x prime is equal to ax. So this is going to have to be a vector because I'm asking for a vector that if I multiply it by a, I get the same thing as if I took its derivative. That's going to have the form x is equal to c1e to the lambda 1t v1 plus c2e to the lambda 2t v2. I don't need to do any work. All that stuff we did with the algebra, with the substitution step and the boiling it down to diagonalization was essentially to argue that this theorem is what you need to know. So if you recall, the way that we extracted this information algebraically was we started with something like x prime is equal to ax, and then I noted that you could write this as s d s inverse x, and then there was this step, ds inverse x, and then we did a substitution where y prime was equal to dy, and we could just observe the solutions to this. The point is, you don't need to do any of that. If you know this theorem, this is exactly the same as when we use the characteristic polynomial of a differential equation. So this is supposed to be analogous to if I gave you a problem like x prime prime minus 4x prime plus 4x is equal to 0. We don't put in a trial solution to that. We just solve it. We write down, r squared minus 4r plus 4 is equal to 0. So r minus 2 squared is equal to 0, which means r is equal to 2 with multiplicity 2. And so the solution has to be x of t is c1e to the 2t plus c2 te to the 2t. The structure of the roots of the equation tell us what the solutions have to be. I don't need trial solutions. I don't need derivations. I just need to know how to take the characteristic polynomial and turn it into a solution. So the same thing is true for these vector equations. So let me write down an application of this theorem with a specific example. And then I'm going to tell you how the picture comes into play. So if I gave you the example of, example 1, if I told you x prime is equal to 2, 3, 0, minus 4 times x. And then I tell you off to the side, you do some work, and you figure out that for the matrix A, which is 2, 3, 0, minus 4, that lambda 1 is 2, and lambda 2 is negative 4, and v1 is equal to 1, 0, and v2 is equal to 1 minus 2, in the same exact way that we can go directly from the characteristic polynomial to the general solution, I can take this information and construct the general solution. The general solution to this vector differential equation looks like x is equal to c1 e to the 2t, because that's the first lambda, times its eigenvector, plus c2 e to the minus 4t times its eigenvector. Once we have the theorem, these are very easy to write down without any derivation. To my mind, the hard part about this is less that the algebra results in this, that you learn this algorithm for producing these things. What I want to do is I want to connect it up to what this is actually showing you, right? So one thing to observe is that the vector 1, 0, if you look at this picture I wrote over here, the vector 1, 0 points in that direction, which looks like a straight line. And if you're careful, you can see that 2, 3, 0, negative 4, this matrix that I've put in up here, is this matrix. So I've turned the matrix into a vector field. So this is going to be a vector field interpretation. Vector field. So the idea is, if I told you x prime is equal to 2, 3, 0, minus 4 times x prime, and I thought about this as coordinates, x and y. No vector now, just an x and a y coordinate number 2. What's that?
Or x prime.
Oh, just x.
Oh.
This equation would say x prime y prime is equal to 2x plus 3y, 0x minus 4y. Thinking about x and y as the coordinates of this vector x. So what we're looking at here is a relationship between an input vector, an input set of coordinates, x and y, and an output vector. And that should remind you a lot of vector fields. So way back in the day when we talked about vector fields, a vector field was a function that ate a point and attached an arrow to it. If I think about the vector field f of x and y is equal to 2x plus 3y, comma, minus 4y, graphically what this vector field will do is if you feed it any point x, y up here, it tells you what direction you're headed. So think about x and y, this x and y here as rabbit population and fox population, right? So two things that are related to each other that are varying with respect to time. They interact with each other, right? So they're moving, but they're interacting with each other. Or you can think about it as the concentration of salt in two tanks that are hooked up to each other. So there's mutual mixing happening, right? Two quantities that are connected to each other. And so every point that you could be at, every x, y value you could be at, is telling you something about that has a value. When x has population 2 and y has population 3, how are those populations changing? And the arrow tells you how they're changing. So if you're at this point, so I guess 1, 1, it looks like your population is increasing in x and decreasing in y because your arrow is headed this way. And it shouldn't be a surprise to you. So when I look at this, I look at this vector field. If I got stuck on one of these straight lines, I can't leave. If I'm on this line, I'm just on it. What direction do I move from here? Well, I go this way, and I go this way forever. This straight line solution, this straight line, is the line dictated by this eigenvector. And the other straight line solution, let's say 1, negative 2, that line is the other line dictated by the other eigenvector. So what's happening here is fundamentally the first thing that this solution structure is telling you is whatever you're doing, you are traveling in a combination of along the line dictated by this vector and along the line dictated by that one. So I'm going to draw this because I had a really beautiful animation set up to show you what's happening here, but I guess I'll draw it first, and then I'll show you what my slides could have been. So let's draw an XY plane.
RTD.
Yo.
For the homework, in the homework we have to know what over damping and critical damping or under damping are. Do we need to know that for the test?
No.
So just do the homework.
Just do the homework. You can come and ask questions. I'm not. So I could talk about that more specifically later on, right? But I don't want to talk about it with respect. That I did not really emphasize the mass spring stuff in the way that like a lot of people do. If I have time at the end, I'll go back and talk about it specifically. I want to do that with graphics, and I just don't have the book set up to do it yet. What was I doing? Oh, okay. So I have the vector 1, 0 and the vector 1, negative 2. Those are my eigenvectors for the problem. And then if I think about, I don't know if I can do some bouncy chalk here. Okay. So what is actually happening if I'm on this line? Suppose that you're a point, we're just going to look at a solution of the form e to the 2t times the vector 1, 0. That's all I'm going to look at. It's e to the 2t times the vector 1, 0. So when t was equal to 0, think about this as solution 1. That's this part. So imagine c2 is 0 and c1 is 1. Then I would be right here when time is equal to 0. I'd be at the point 1, 0. What happens as t goes to infinity? Where does that point go? It's got to go out to infinity, right? T gets bigger, e to the 2t gets huge. This thing is accelerating out this way. So as t heads to infinity, you go that direction. What if t goes to minus infinity? Where does the point go?
Backward, the other one.
Backwards where?
Along the 0 axis.
Where does it limit to?
Infinity. Oh, 0?
0, right? E to the 2t when t is negative is like 1 over e to the something huge, which is close to 0. So you can travel from this point at the origin. So this is t. You shouldn't tell anybody I did this. T equals negative infinity. You would sort of be at 0, and as time evolved, you're heading along the curve this way, right? As time evolves, you start at this point, and then you head that direction. What if you're on the other axis? What if c1 was equal to 0 and c2 was equal to 1? Then your second solution would look something like e to the minus 4t times the vector 1 minus 2. So you would start here. Where do you go? Time goes to infinity. What direction do you travel as time goes forward? Down or up?
Down.
E to the minus 4t goes to 0 as t goes to infinity. So you head this way as t tends to infinity. And here, t is equal to minus infinity. It would be way out here on this line somewhere. So you're traveling this way along this line as time evolves. So the idea is, if I take those 2 points and I add them together, like vector math, then any combination of those 2 things I get is going to be, it's almost like this is setting up a coordinate system. The idea is, this is what happened when time was equal to 0. This solution was here, and this solution was here. As time steps forward, this point moves up, and that point moves this direction. So they start, the combination of these 2 things starts here. That point would represent e to the 2t 1, 0 plus e to the minus 4t 1, negative 2. That's the way vectors add, right? So you would start here at times equal to 0. As time evolves, this point might go from this position to this one. And this point might move from here to here. So the combination of the 2 must move here. So basically what the solution is doing is it's giving you a coordinate system that describes every possible answer. Every motion along that path is dictated as this point comes up and this point goes out. This is the combination of those 2. So you can see as these things slide this way, that point should be here. As time continues, the point's going to be here. As time continues, the point's going to be here. And it's going to be accelerating away from 0 because this is exponential. So it's really getting out there pretty quickly. Yep.
So in this in your example graph, there should be the 3 of these sections should just not exist.
How could you get up into this section? So I chose C1 is equal to 1 and C2 is equal to 1, which put me up here. How could I have started with initial conditions up here? Different C1s and C2s, right? So different combinations of positive and negative C1s and C2s will put you into different quadrants. So this is basically, and the job of an engineer in practice is, this is what you interpret. This picture is what you get to interpret. So often, the actual quantitative solutions are less important than the description of every possible output to the system. So when I look at this with sort of a macro eye, without knowing anything about what the solution actually is, I can tell you, okay, so there's some kind of equilibrium position here in the middle, and as I move away from it, I get sucked into these sort of asymptotes that are sailing away. So it's sending things away in this direction, but things are coming in this direction. So it's kind of like a saddle point almost. And we're asymptotic to this straight line solution. So we have this straight line solution is throwing the solutions away, and this straight line solution is pulling them in like an asymptote as t goes to infinity. So the qualitative analysis of the picture turns out to be more important in a lot of cases than the actual solutions, because this is every solution. And the stability of those solutions is all in the same picture. So this move of taking a differential equation and turning it into a vector field is called making a phase portrait. And that's actually chapter 9.9. So I thought I would sort of introduce it now because I think it's a good way of viewing, I mean, this kind of picture where we're thinking about the curves, this is a good way of viewing what these differential equations are actually doing. And actually, you can tell a lot about the structure of a matrix or the behavior of the solutions without ever even knowing what the solutions are. So I'm going to write one in that has complex eigenvalues. What do you think is going to happen?
Rotation.
Computer's gonna crash.
Yeah, well, okay, computer could crash. It could. It's like it's going to say, oh my god. I'll give you the exact one from your exam, which I think was this. 3 minus 4, and then this corner was a positive, so there's a 4x and a minus and a 3y is what that turned out to be, except I've completely mangled that. 4x plus 3y. Okay. Okay, so if you remember from your exam, I think the eigenvalues was something like 2 plus or minus 3i. I think that's what they turned out to be. So the 2 was like an e to the 2t. That grows as time goes along, right? So this is why you're spiraling away from the origin, right? The exponential part is making it grow away from the origin, but the other part of it, the sine and cosine part, is giving you these twists. Okay, so this is called a spiral solution. So complex eigenvalues in your matrix, you're always going to be diagonalizable because there's going to be 2 distinct eigenvectors, but that corresponds to no straight line solutions. Everything turns. If you have, instead you use minus 3, minus 4, I mean to put I think a negative here as well, that should reverse the spiral because we have a negative real value of the exponential. So here, we have another spiral point, but one that is attracting solutions instead of throwing them away. So, a differential equation, an x and a y, that were related by that matrix. So, if we wrote down the matrix that corresponds to this, so that would be the problem. X prime is equal to minus 3, minus 4, 4 minus 3x. That matrix will turn out to have complex eigenvalues. The in fact, I believe it has the lambda is equal to minus 3 plus or minus 4i is what that will turn out to have. So the real part turns into a negative exponential, which is going to 0, and the imaginary part is the sine and cosine part. So all of the behavior of these diagonalizable matrices can be recorded, observed by checking these vector plots. And a lot of the point of chapter 9.9 is to classify these equilibrium points. Okay. Now, unfortunately, or fortunately, and depending on how much you like bad things, not every matrix is diagonalizable. Yeah, I know. So I'm going to write down a different system now. One that, I guess, yeah, I won't try to show you my animation because my animation is, this computer won't run it. So let's look at example 2. And we'll see if we can observe some behavior that differs from what we've seen so far. So we've seen no straight line solutions and just pure rotation. That happened when we had complex eigenvalues. And then we had 2 straight line solutions when we had 2 real eigenvalues. So what if we have a defective matrix? So I'm going to write down this problem. So let's consider, I can find page 3, 4, 3. Okay. Let's look at example 2. X prime is equal to 0 minus 2, 2, 4x. This vector differential equation. Now, if I wrote this down in that sort of coordinate form, x, y is equal to 0 minus 2, 2, 4, x, y, then I would have x prime, y prime is equal to minus 2y and 2x plus 4y. And so I'm going to write down the vector field f of xy is equal to minus 2y, 2x plus 4y. That is the vector field that tells me if I'm at a point what direction I should move. I say 0 x's and minus 2 y's and 2 x's and 4 y's. So the first observation I make, without doing anything to the matrix, if I just naively wrote this system and put it into the vector field calculator, and I look at the matrix, what I'll notice here is that it looks like I have one straight line solution this time. Just one. Not two. One direction that's being preserved. So if I only have one straight line direction, that suggests to me that I only have one eigenvector. Right? The matrix can only hold one direction constant. So let's take a look and see. Hopefully at this point it's okay for me to...
Even in the spiral case, this is where eigenvectors?
Those were complex eigenvectors, right? So the complex eigenvectors tell you about the rotation. So real eigenvectors tell you in like the directions that don't change in the real plane. So if there's two real eigenvectors, there will be two lines that are the straight lines that get preserved by A. If there's one eigenvector, there will be one, there it is right there, one direction that gets preserved by the system. So each straight line corresponds to one real eigenvector. And it's not possible for a 2x2 matrix to have one real and one complex eigenvector. Right? There can't be a rotational component because those have to come in pairs.
But how'd you know the line was going up?
Part of it is I'm looking at, like, you see how all these things are parallel to each other?
Yeah.
So that parallel line it's a structure of this type of problem that every solution turns out to be asymptotic to that straight line solution. So all of these, notice, every single one of these ends up in the end looking like the straight line solution. If you start here and you spiral out, you end up looking like you're traveling, all of this is in the same direction. If you start here and spiral this way on the other side of the line, you're headed down, but you still look like you're all of this vector field away from the curling point. It's all parallel to itself. Okay, so I guess the first thing to observe here is that the matrix A, which is 0, minus 2, 2, 4, has lambda is equal to 2 with multiplicity 2. But the geometric multiplicity of that eigenspace is just 1. It has one linearly independent eigenvector. So, for example, the eigenspace could be written as the span of the vector 1, negative 1. So just one eigenvector. So the first thing I'm gonna do is I'm gonna show that the solution that we want to be a solution still is one. If we were working in this case, so back in the case where we had stuff like x prime prime minus 4x prime plus 4x is equal to 0, if I wrote down r squared minus 4r plus 4 is equal to 0 and got r minus 2 squared is equal to 0, I could immediately write down that one of the solutions was e to the 2t. Right? I'm going to say the same thing here. I'm going to guess that I can immediately write down one of the solutions here as, so solution 1 is x1 is equal to e to the 2t times the vector 1 minus 1. I'm guessing that's a solution. In the same way that I could use the characteristic equation to get one solution immediately with no extra work, I can use the eigenstructure of A to get as many solutions as I have eigenvectors for.
So can you put a C1 in front of that, or is that just
We could put a C1 here. Yeah. So this is a sort of a general solution. Remember, I'm going to put the C's in when I combine them up to be the full general solution later. For now, I just want to test and actually make sure that this is a solution, because I think it will give another hint as to what the eigenvalues and eigenvectors are actually doing. So I'm proposing that the first fundamental solution to this differential equation says start on the line dictated by the vector 1, negative 1, and then travel like e to the 2t. Start on the line dictated by 1, negative 1, and then travel like you were e to the 2t. So just like if you're on this side, you go this direction. If you're in this side, you go that way. That's the fundamental solution. Start on the line, stay in the line. Well, let's see. The claim here is, if that's going to be a solution, it should be the case that if I plug this into both sides of the equation, I should get the same thing, right? So let's actually demonstrate that. If you took the derivative of this thing, so you take e to the 2t times the vector 1 minus 1, and you take its derivative, that vector is constant. You don't take a derivative of constant, you take a derivative of the moving part. 2e to the 2t times the vector 1 minus 1. On this side, we get an extra copy of 2 that came from taking the derivative of this exponential. What about the other side? 0 minus 2, 2, 4 times e to the 2t times 1 minus 1. Well, scalars factor out of matrix multiplication. Wait a second. I said that 1, negative 1 was an eigenvector for that matrix, with eigenvalue 2. So without doing any multiplication at all, what must come out here?
2.
2 times 1 minus 1. That's what happens to an eigenvector, right? So the 2 on the right-hand side came from the fact that this is an eigenvector, and the 2 on the left-hand side came from the exponential with the eigenvalue. That's kind of how there's the interplay between the derivative side and the eigenvector side of this equation. All right, now comes the obnoxious part. I mean, more obnoxious. What did we do in this problem when we had repeated eigenvalues? Where did we get another solution? What did we do? We do what? We put it, well, the independent variable here is t, so what are we going to stick in front this time? We're going to stick a t in front, right? If I want another solution, I take my original solution and I just slap a t on there, and then I can check with the Wronskian that works. So what we're going to do now is we're going to do a fancy version of putting a t into this. So the solution will turn out to basically correspond to modifying this original solution in a way that picks up an extra copy of t. You should not be surprised when that happens. The method I'm going to use to show you how that works is one that I will do one time, and then I'm going to hint at something called Jordan canonical form. So, I do not have time, of the many things I don't have time to talk about, here's another one. So all of this is all of what we're going to do next is part of what is called Jordan canonical form. In the 2x2 case, it says the following about all matrices. If A is 2x2, either A is equal to S D S inverse, where D is lambda 1, 0, 0, lambda 2, and S is equal to some eigenvectors. That's case 1. If it's diagonalizable, you can diagonalize it. Or A is equal to SJ S inverse, where J, the middle matrix looks like this. Lambda 1, 0, lambda, where lambda is the eigenvalue. Because the only thing that can happen is you can only have a defective matrix if the eigenvalue repeats, right? So every defective matrix can be sort of fake diagonalized. Because that matrix is not diagonal, right? It's almost diagonal. So you can sort of fake diagonalize A, where the matrix that goes in the middle has this form, and the matrix S has the rather obnoxious form V1, which is an eigenvector, and V2, which is a mystery vector. This dude right here is going to be called a generalized eigenvector, and what I'm going to do next is going to hint at one of the ways you could discover this thing. So, I want to point this out for those of you that are going to be doing lots of linear algebra in the future. The study of matrices with repeated eigenvalues comes up all the time in applications, and I just want to let you know you could spend a year studying Jordan canonical form and the structure of matrices. I'm just going to suggest that that's a thing. So what do you need to know for the test? I mean, not this either. All right, so how would we solve this problem? Suppose you had no technique available, and we have none. And somebody writes down xy is equal to 0, minus 2, 2, 4, xy, and there's primes over here. And you say, I have absolutely no idea. I can't use matrices. It's not diagonalizable. I've got one linearly independent solution. I have no idea. So it turns out what you do, if you remember back in section 9.1, I pointed out that there was a way that you could turn any higher order equation into a system by doing a substitution. And somebody in here asked me if you could go backwards and turn a system into a higher order equation using substitution. And that's exactly what we're going to do. We're going to take this, and we're going to take this equation, we're going to get all the y's out of it. So we're going to attack this with substitution. Attack. And then what you're going to be hoping when we're finished with this is that there's another way to do this. So, what substitutions can we make? Well, if x prime is equal to minus 2y, then anytime I see a y, I could write a minus 1/2 x. Remember, I want to get it's this equation is the thing I'm trying to get all the y's out of. So, that y I could replace with minus 1/2 x, because that's the first equation.
Minus 1/2
Prime.
Okay.
I also have to get rid of that y prime. How am I going to do that?
Take the derivative.
Take the derivative. Anytime I see a y prime, I could replace it with a minus 1/2 x prime prime. So what I'm going to do is I'm going to take this, and I'm going to replace that, and I'm going to take this, and I'm going to replace that. So the result of doing that substitution looks like this. Minus 1/2 x prime prime is equal to 2x plus 4 times minus 1/2 of x prime. And if you take that and you clear the fractions out and you put it all on one side of the equation, you end up with x prime prime minus 4x prime plus 4x is equal to 0. And I know how to solve that equation. I've conveniently written the beginning of it over there in purple. So this is an equation I can decide. There's no system anymore. This is just one differential equation. It's a second order linear differential equation with constant coefficients. I can write down its characteristic. Oh, it's the same exact equation. Imagine that. So since I know the characteristic equation, I know that the solution to this is solved as x is equal to c1 e to the 2t plus c2 t e to the 2t. I can just solve this using those techniques. Higher order linear constant coefficient differential equation. Now the last thing I have to do, having solved this, is I better be able to have an expression for what y is equal to as well. Angel.
Where did you get the double prime from?
Right here. I took this equation and I took its derivative on both sides. If y is equal to minus 1/2 of x prime, then y prime is minus 1/2 of x double prime. I mean, if two functions are equal, their derivatives are equal. It's like it should feel like cheating that I did that. So what's y equal to? Because I need x and y to solve this equation. Oh, look! Y is equal to minus 1/2 of x prime. Okay, so x prime is 2c1 e to the 2t plus c2 e to the 2t plus 2c2 e to the 2t. But that's not y because y was minus 1/2 of x prime. So y is equal to minus 1.
Wait, the second part had a t, right?
Oh yeah, there's a t. Yep. Okay, so I'm going to multiply all this by minus 1/2, and I'm going to get minus c1 e to the 2t minus 1/2 of c2 e to the 2t minus c2t e to the 2t. And now we ended up with the particularly obnoxious looking final answer. Xy is equal to c1 e to the 2t plus c2 t e to the 2t and minus c1 e to the 2t minus 1/2 c2 e to the 2t minus c2t e to the 2t. And I have one more out. I mean, this is all written on my notes if you guys, when I post these, if you don't want to like scramble to try to get it all written down. I'm recording it as well. Yep.
Can you absorb the negative signs into the C1?
You
and
can't
C2?
because the problem is the C1 and the C2, this C1 and the C are the same. So if you absorb the negative here, you make one show up here.
Okay.
Yeah, so you have to be really careful. Like those basically tell you what the blend of solutions need to be after you choose your arbitrary constants. The last step I'm going to do here is I am going to slightly simplify by, I'm going to take, you notice these have c1 and e to the 2t inside of them, so I could write this as c1 e to the 2t times the vector 1 minus 1. That shouldn't be surprising because we already saw that was a solution. That was our first solution. And if I do the same thing to the second bits, I take out the c2 and the e to the 2t, what's left behind is a vector 0 minus 1/2 and then a t times the vector 1 minus 1. And that's the bit that shouldn't surprise you. c2 e to the 2t, this actually probably be more illustrative if I did it this way. Hold on. I'll do one intermediate step. c2 e to the 2t times the vector 0 minus 1/2 plus c2 t e to the 2t times 1 minus 1. I want to draw your attention to this. c1 e to the 2t and c2 t e to the 2t. This has the same structure as the repeated root thing did from the characteristic polynomial, right? This characteristic polynomial, we had a solution that was the fundamental solution and then t times the fundamental solution. Here we've got kind of the same thing. Fundamental solution, t times the fundamental solution, but then this extra annoying thing. And we need this extra part because these have the same direction. They're not picking up some different direction in the eigenspace. This is still just sitting in the same one-dimensional space. So if I go one step further and I write this abstractly, what we've gotten here is that our solution x is c1 e to the 2t v1, where v1 was the eigenvector, plus c2 e to the 2t times v2 plus e to the, t v1. That form right there turns out to be the general form for defective matrices in the 2x2 case. This is the general form. You diagonalize the matrix, you find the eigenvalue, and then it's more delicate than just there's some eigenvector. There's a relationship here between this mystery vector v2 and this v1, which is going to turn out to be an eigenvalue. v1 is an eigenvalue, or eigenvector. v2 will turn out to be something called a generalized eigenvector. So, in the setup that we did right here, we got the answer as a consequence of all this algebra that we did, right? We wrote down the answer, we multiplied a bunch of matrices together, and when we were done, we could see V1 and V2. We can just read them off. The process that we're going to invent, which I'm not going to do today because it's just kind of an algebraic slog to set it up, there will be a much easier way to do this. I don't want to have to do a bunch of algebra to find this vector. I want it to be part of the matrix itself. When we had a diagonalizable matrix, we could just write down the answer by knowing the eigenvalues and eigenvectors. I want that to be true in this case as well. I don't want to have to slog through this to find the answer. Okay, so then the question becomes, how do we find if every one of these has this solution? If it's the case that x is going to be equal to c1 e to the lambda t plus v1 plus c2 e to the lambda t v2 plus t v1, how do we find v1 and v2?
V1 is an eigenvector.
But we have to be careful. The method we're going to use is we're going to discover V2 first, and then we're going to find the V1 that goes with it, because there's lots of eigenvectors, right? There's lots of eigenvectors. I'm going to need a precise scaling of this eigenvector to go with the vector V2. So we're going to come up with an algorithm where the first thing we do is discover V2, and then using V2, we'll be able to extract the correct eigenvector V1. Now, I guess the upshot here is I want you to think that solving for these things in specific cases to get this kind of structure is fussy. Probably it seems fussy and highly dependent on the structure of the matrix. But you could have gotten almost everything we said here. The matrix is defective. There's one straight line solution. What happens as t goes to infinity? What counts? Well, this part does whatever it does, but this dude over here with the t in front of it, that's going to dominate everything, because now we've got an exponential times this value t. So the most important term in the entire solution is this tv1 term right here, which is why all of these are parallel when you get far enough away. And I didn't need to do any of this to figure out what was going on from the picture. If you fire up MATLAB, industry standard language, you should all learn it. If you fire up MATLAB or something, or Wolfram Alpha or Mathematica or whatever, Python, and you start studying these things, you can get almost all the information you need numerically by analyzing this. Qualitative analysis. All right, so I'll let you go. Next time what we'll talk about is, so I can actually start next time. I will show you the algorithm for finding the defective matrices, and then we will come back at some point either tomorrow or Thursday, and I will talk about the damping, the damping scenario, because that is something I wanted to put more time into, like the critically damped, underdamped. It's easier than you think it is.
Considering I should just wait for class.
You can wait for class.